Hi, we're going to continue our discussion of thermodynamics, and we talked about work. Now we're going to talk about heat. Heat's another way to move energy. So the two ways to move energy are by doing work on or by the system, or by allowing energy to flow in or out of the system in the form of heat. So heat is the transfer of energy as a result of a temperature difference. So we know if something's at a higher temperature next to something at a lower temperature, heat will flow from hot to cold. The second law of thermodynamics will help us understand why it always goes from hot to cold and not cold to hot. So we're going to use the same sign convention for heat that we use for work. So if the system loses energy by allowing heat to flow out to the surroundings, then its internal energy goes down, and so we'll say that Q is negative. And if energy flows into the system, its internal energy goes up, so we'll say the Q is positive. When we're talking about these processes, diathermic is a process that heat is allowed to move, so an open container or non-insulated container, I should say. Adiabatic is a process where you don't allow heat to flow, so you keep it in some sort of insulated container when your reaction takes place. So, important difference. So, heat and work are very similar in that they're kinetic energy being allowed to move into or out of the system. Two words you should remember: an exothermic process is a diathermic container releasing energy as heat to the surroundings, and then endothermic is you have it in a diathermic container, it absorbs energy as heat from the surroundings. And so heat is a mode of transfer of energy that achieves or utilizes random atomic or molecular motion in the surroundings. So we had a similar picture for work. Work would have been lifting, if this is a ball, up, applying a force over a distance. That's taking advantage of coherent motion. All the kinetic energy in the same direction as you want to move the ball is transferred, and the whole ball moves. Whereas heat is the process where random motion is transferred to or from the system. And so the particles move randomly as a result versus in one direction. And so their temperature goes up, but you don't move the whole system. So in order to measure heat flowing in or out of a system, we need to know something about the heat capacity. So the heat capacity is a measure of how much heat it takes to change the temperature of something. And so it's going to be determined on what the substance is, what its phase is, all of those things. But once you know C, that heat capacity, then you can use that for your system in order to determine Q, how much heat flowed into or out of the system, maybe during a chemical reaction. So this first one, self-test 2B.1, you have the heat capacity of a 1 kilogram block of iron is 4.49 kilojoules per Kelvin. What's the value of Q when the block cools from 30 to 20? So 1 kilogram, here is our heat capacity. Temperature changes from 30 to 20. We have a temperature change in Celsius. We multiply it by the heat capacity and we get negative 45. Notice I also did that temperature change in Kelvin because that's the units of our heat capacity. But if I add 273 to both T2 and T1, they'll just subtract. And so because a degree Celsius is the same size as a degree Kelvin, the two scales are just offset. The temperature difference in Celsius and Kelvin will always be the same, so you don't have to go through that conversion. It is true, and we won't talk too much about it in this topic, but the heat capacity, well, first let's talk about these two words. Specific heat capacity, because notice up here, we don't have it per quantity. Usually you talk about, if you're talking about a substance, the heat capacity per some amount. So the specific heat capacity is the amount of heat it takes to change the temperature of 1 gram. And the molar heat capacity is the same thing, except you put it in units of heat to change the temperature per mole. So usually you'll find these in tables, but you often find specific heat capacities too. A little table of heat capacities to show you, for one thing, liquid water has a super high heat capacity. That's why we use it to cool our cars with our radiators. It's a very, very, very high heat capacity. It takes a lot of heat to change the temperature of water. We're not going to focus a lot on this, but it's important to understand for the future that if you have gases, the heat capacity depends on whether you carry out the process at constant pressure or constant volume. And actually in the next little section, in section C, we'll talk more about why that's true. So just stop and do this problem. I set it up for you. It says when energy as heat is needed, or what energy as heat is needed to increase the temperature of 250 grams of water, 40 degrees Celsius. Just go up here and get the specific heat, multiply by the grams, and multiply by the temperature difference, and you'll come up with Q. So calorimetry is how you measure the heat released or absorbed during a process. And it's some sort of insulated container. So in Gen Chem, you probably used a coffee cup calorimeter. In this class, you'll use a bomb calorimeter, which will be more exciting. And it's a slightly different process, so we'll talk a lot about that when we do that lab. So read this toolkit. Just reminds you of the units of electricity and how they're related to heat and therefore work. So to use an electric heater, which you can use to calibrate a calorimeter to figure out what its heat capacity is, you need to remember that a joule of energy is equal to C charge in coulombs times volts. So read through that and that will remind you. But if you use an electric heater, you can determine the heat capacity because you can use a current of some heater that has a voltage and apply that for a certain amount of time. And from this calculation, you can calculate how much heat you added. From the amount of heat you added, you can plug it in here, divide by how much the temperature changed of your system, and you'll get the C, the heat capacity of your system. So that's a common way to determine the heat capacity. So remember, once you have the heat capacity, you can use it to calculate Q for any reaction. So that's one way to do it. The other way to do it, which is very common, and you're going to do it this way, is you could burn a substance, like in your bomb calorimeter, if that's the calorimeter you're using. And if you know the Q, then you can plug it in here, determine delta T by measuring it, and also get the heat capacity. So 2 ways to measure the heat capacity: with an electric heater or by burning a substance where you know how much heat's going to be released. Stop and do this little self-test. It's also very, very simple. So do self-test 2B.3. And then also do this one. They're both very, very easy problems where you use this equation, get Q, and then from that, you can calculate a Q for combustion. So do both of those. They both give the answers. You can ask me if you have any questions. Then the last little section is just on the fact that during an expansion of a gas, it's going to be true that if you do an isothermal expansion, that the kinetic energy is going to stay constant. So kinetic energy is proportional to the temperature. And if the temperature doesn't change, that means the kinetic energy doesn't change. If it's a perfect gas, then all we have is kinetic energy, because the potential energy is the interaction energy, which we say is 0 in a perfect gas. So that means if the kinetic energy is a constant, then delta U equals 0, and internal energy doesn't change. 0 equals Q plus W, therefore Q has to equal minus W. So when you look at this self-test, what influx of energy, so it's right up here, as heat accompanies the free expansion of a perfect gas. Free expansion means that external pressure is 0. External pressure is 0, then there's no work. If there's no work, there's no heat, and so it's 0. You could also think about an isothermal expansion of a perfect gas done reversibly, and then you'd have to know what temperature and the final and initial volume, and then you could also calculate Q. So Q is going to depend on how the expansion takes place, because it depends on how much work is done. There's a different amount of work against a vacuum, which is 0, versus some constant pressure versus reversibly, where the pressure stays equal to the gas pressure throughout the process. So that is it for heat. And we will come back and talk more about enthalpy in a second.